Possibly the biggest problem with just constructing your action any way you like this, and then putting things on a grid and making up some more Lagrange equations, is that you have no guarantee that your resulting mechanics is going to obey the principle of special relativity. The easiest way to do that is to always embody all of your physics in terms of tensor relationships and tensorial objects. Now this thing here is a scalar, so it should be constructed, if you're going to construct it out of fields that are vectorial or anything like that, it should always be explicitly scalar-like. But we have an even deeper problem here, because you see our Lagrangian, even if our Lagrangian was a scalar, we've got a time integral here. So in other words, this seems to be frame dependent. We have to write this in a way that is explicitly not frame dependent for fields. So supposing I have something like a 4 vector, like this electromagnetic potential, and I want to construct scalars out of it, a natural thing to do is to contract over itself. And because that's an inner product, that is a scalar, and so it's the same in all inertial reference frames. Remember, this thing here is a function over space, and so therefore another thing I could do is I could take a derivative. And so this thing here is also a scalar because I'm summing over the alphas. So I can get terms like this and I can construct scalars out of them. Now a natural way of constructing the Lagrangian, note that this kind of term is actually a function of space. And so a natural way of getting the Lagrangian is to integrate those kinds of terms over all space. And so those kinds of terms will be a Lagrangian density. Integrate them over space, you get the Lagrangian. Now you'll note that this is integrating over 3 space. And so that is clearly not Lorentz invariant either, because these kinds of things here are scalars. This thing, the volume element depends on whether you're in a particular reference frame. So therefore this Lagrangian is going to depend on what frame I'm in. However, the Lagrangian precisely is not the physical thing. The physical thing is the action, where we take the Lagrangian and we integrate it over time. So the action is going to be the integral over time over the Lagrangian, which is the integral over space of the Lagrangian density. And therefore the Lagrangian is the integral over 4-dimensional space-time of the Lagrangian density, and that is a manifestly invariant object. So this action is indeed a scalar. So if we break it down for terms like this, then our action is going to be an integral over all space-time, and our Lagrangian density is going to be a function of our fields, whatever they may be. It's also going to be a function of the derivatives of those fields, and it might be a function of our actual space-time itself. But typically we don't have it being a function of our space-time, it's just a function of our fields and their derivatives. And then if we demand that we have the principal least action for this, we can redo our derivation of the variational principle, except now it'll all be one step higher in dimension because these things are fields, and so instead of being variables, they'll be functions, and so it's like functional variations. And I'll just give you the result of that rather than go through the derivation. So this would be your Euler-Lagrange equation. If we look at this, this is just a function of alpha on both sides. So it's vector based. There's actually 4 equations here. And what kind of equations are there? They're actually partial differential equations instead of ordinary differential equations. This thing here is the Lagrangian density, which is going to be defined in terms of scalars, which makes this manifestly invariant. And our action is therefore also going to be, because it's the integral over space-time of scalars, that's also going to be invariant. Now remember, back in classical mechanics, if you have a variable and if you take the derivative of the Lagrangian with respect to one of those variables, then you assume all the other variables are constant. You also assume that all the derivatives are constant. And likewise, if you take the derivative of the Lagrangian with respect to one of these derivatives of the coordinates, you assume that all the coordinates themselves are constant. And just the same down here, if you take the derivative of the Lagrangian density with respect to one of your field variables, you assume the others are constant, and you also assume that all the derivatives are constant. And if you take the derivative of the Lagrangian density with respect to a particular derivative of a particular field component, then you assume that all other derivatives of all other field components are constant. So we're really starting to see how the principles of, say, special relativity really constrain our classical mechanics as well. Our classical mechanics for fields must be of this kind of form. And we're going to have some practice with this, so we'll have some practice in our next few lectures in dealing with Euler-Lagrange equations for fields, and we'll have some practice looking at, say, relativistic quantum mechanics and how relativity really affects our theory of quantum mechanics. And we'll also come back to this idea of principles and see how principles really affect the kinds of theories we can come up with. And we can in fact predict things like the form of electromagnetism from pure basic principles of symmetries.